Okay, we are beginning section 12.4. Only 3 sections left in this summer session. So 12.4 has to do with the standard deviation and z-scores in normal distributions. Standard deviation plays a crucial role in normal distribution. I know you can read, but I'm going to read it anyway. Summarized by the 68, 95, 99.7 rule. I'm going to show you this illustration here in a second, but I want to read this. This little this box here describes it all. 68% of data items fall within one standard deviation of the mean. So if the mean is here, then 68% of the data falls within one standard deviation of the mean. That's what that is saying. And when I show you the next little illustration, it'll make more sense. But 95% falls within 2 standard deviations and 99.7 fall within 3 standard deviations of the mean. Looking at this illustration here, this is what that means visually. Okay, we have this thing right here called a bell curve. Because it's shaped like a bell, obviously. Okay, in the bell curve, the mean is right there, the middle of it. Okay, what this means to you and to everybody in the whole world is that when I look at this, most of the scores will fall within 68% or one standard deviation of the mean. 68% of them have values will fall within 68%. And then 95% fall within 2 standard deviations of the mean. But before I go any further on this, I want to talk about one of the misuses of this and what I have run into. When I was in college, I had a geography class, and my instructor graded on a curve. Okay, and I'm sure that some of you have heard about grading on a curve before, and we really, if you ever hear somebody ask to be graded on a curve, you don't want that to happen. Okay, what that means is this. I'm going to redraw this drawing here as best I can. It looks like this. Okay, so if I'm grading on a curve, this area right here, the 68%, that's where most people would fall if I were talking about grades. That means that 68% of a class would get a C. Okay, that's all of these people in between here. These people out here in 2 standard deviations would get a D, and these out here, the last 0.3% would fail. Same thing out on this side. 2 standard deviations would get the B, and then out here, they would get an A. What that means is this. If I have a class of 10 people, or let's say, better yet, how about 100? Let's say these are hundreds. That would make it easier. Okay, 68%, or roughly 70% of the students would get a C, or 7 out of 10. Okay, that means that from here, there's our A, here's our F. Okay, and let's go ahead and make this easy. This is our D, and this is our B. And then in between here, the rest of these people all get C's. So if you're asking to be graded on a curve, you're actually asking basically to get a C. Which when everybody does poorly on a test, that's when you hear, well, can you curve this or something like that? And although it helps you when you do poorly on a test, it really does not help you, because if these were percentages, the 100% would get an A, 90% would get a B, and then everybody else below 90%, 89 to 21, will get a C. And that means that someone who scores a 21% would get the same letter grade as someone who scored an 89%. And does that sound fair to you? That's what the main thing. It's not a fair deal. Male adults in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Find the height that is 2 standard deviations above the mean. And all that means is this: if the standard deviation is 4 inches, 2 standard deviations is 8. So 2 standard deviations above the mean would be 78. 3 standard deviations below, well, 3 times 4 is 12. I would take 70 minus 12, or 58 inches. Okay. So male adults, most male adults fall between 66 inches and 74 inches. 70 inches is 6 foot, right? 6 times 12 is 72. So 6 foot is 72 inches right there. 6'2" is here, and then 6 foot, 5'10", 5'8", 5'6". So most adult males fall between 5'6" and 7'2" or 6'2" inches. Computing z-scores. A z-score describes how many standard deviations a data item in a normal distribution lies above or below the mean. The z-score can be obtained using this formula right here. Data items above the mean have positive z-scores. Data items below the mean have negative z-scores. A z-score for the mean is 0. So let's look at this example right here. I got to pause for a second because I'm going to sneeze. And I need to go blow my nose. Sorry about that. But back to our examples here. Suppose that a certain location and time frame, the mean weight of a newborn infant is 7 pounds and the standard deviation is 0.8 pounds. The weights of newborn infants are normally distributed. Find the z-score for a weight of 9 pounds. So to find the z-score, remember, it's the data item minus the mean divided by the standard deviation. So I have the I lost my pen when I did that. Okay, so we've got 9 minus the mean, 7, divided by the standard deviation of 0.8, which is 2 divided by 0.8. Now this is where, especially when you're doing z-scores, you want to grab your calculator. So I've got 2 divided by 0.8. 2 divide 0.8 is 2.5. This is my z-score. Okay. And what that means is this. When I look at this bell curve that I've been talking about, here is our mean. The z-score is 2.5 standard deviation. So 1, 2, here's the third, 0.5 right in there. Okay, it's 2.5 standard deviations above the mean. Okay, 7 pounds obviously is 7 minus 7 equals 0 over 0.8 is still 0. So it's the mean, okay? A z-score of 0 is the mean. 6 pounds, 6 minus 7 over 0.8 is negative 1 over 0.8, which is 1.25. But remember, it's negative. So the z-score of 6 pounds is negative 1.5 right in here. Standard deviations below the mean. Okay, now we're going to talk about percentiles. If n% of the item in a distribution are less than a particular data item, we say the data item is in the nth percentile. If you remember doing any of your standardized testings, you might remember that, for example, on the ACT, the math portion, if you got a 21 on the math, you were in the possibly 84th percentile is how they would say it, okay? What that means is 84% of the scores were below the 21. So we're going to talk about quartiles now. And I'm going to come back here because it says to find the first, second, and third quartiles of this data right here, okay? The second quartile is the mean. It is right here, okay? That's the second. We always talk about these, and you have talked about the mean or the median, whatever, are all the same when we're talking about the standard deviation. So the mean is the second quartile. Okay. We're going to talk about finding the first and the third, and I'm going to go to my calculator now and put in these values. I'm going to show you again what we did the other day with our calculators. I need to put in these values. I'm going to write these down so that they'll be here when I call up my calculator. I've got 3, 5, 6, 7, 7, 10, 12, 13, 15, 16, 17, 19, and 21. Okay, I'm going to grab my calculator and show you how easy this is. Remember, we are going to go to, that, edit, and I'm going to clear this out. Clear, enter. Okay, and then I'm going to put in my values that I have over here to the right. I've got 3. For some reason, this isn't showing up on your screen. I'm going to go back to here. It's showing up there, but it's not. I got to do something. I'm going to stop sharing for a second. I may have ruined myself. Let me share again. I want to share this. Share. And there's my values. 3, 5, 6, 7, 7. So I've got 3, 5, 6, 7, 7, 9, 10, 12, 13. 9, 10, 12, 13, 15, 16, 17, 19, 21, 15, 16, 17, 19, 21. Down arrow, up arrow. Okay, once you have your data in here, okay, go back to stat. Calculate one variable stats, one. From the list L1, calculate. Okay, remember our mean 11.42. Okay. But when we come down here, we've got our Q1. Hey, look at that. Quartile 1 is 7, the median is 11, and the Q3 is 16. Okay, so there is our information that we are looking for all right in this little piece right there. Okay, Q1, U1 is 7, Q2, or the median is 11, and Q3 is 16. So that's how you find your quartiles. The last part of the thing we're going to do is called the margin of error in a survey. If a statistic is obtained from a random sample of size n, there's a 95% probability that it lies within 1 over the square root of n times 100% of the true population percent, where plus or minus 1 over the square root of n times 100 is called the margin of error. Okay, so if I have the sample that I just used right here, I count up the number of elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 is my n value. Okay. The margin of error is 1 over the square root of 14 times 100%. So then I grab my calculator again, and I'm going to go to the math part. I've got 1 divided by the square root second x squared 14. I'm going to press enter here because I want to do 1 over the square root of 14. And then I'm going to take that times 100. And it is 26.726 is my margin of error. Okay, that is it for this section. If you have any questions, please email me. We can get them solved out. Thank you.